In this video, we are going to discuss about phases of compiler in compiler design course. So basically a compiler is a system software which will be converting a high level language into a low level language, that is a source program what we are giving into a machine language, that is machine language in the sense which converts into zeros and ones. So for converting the source program to machine language, we usually require several phases to convert this source code into machine code. So here we are going to discuss about that. So here we have 6 phases for converting a source language to a machine language. So we are going to discuss about these 6 phases with a simple statement in our C language. So the first phase in compiler is lexical analysis, and the second phase is our syntax analysis. Third phase is semantic analysis, and the next phase, which is fourth phase, is intermediate code generation, and fifth phase is our code optimization, and lastly we have our code generation. So among these 6 phases, the first 4 phases is said to be as synthesis phase, where the source program is being analyzed and it gets converted to an intermediate intermediate code. So this is either called as front end phase or it is called as synthesis phase. And the next 2 phases of compiler is called as analysis phase. So the first phase is called as first phase lexical, syntax and semantic, and ICG is called as front end, and the last, which is code optimization and code generation, comes in the back end, which is analysis phase. So with these 6 phases only, we will be able to convert a source language into a machine code, that is zeros and ones. So here we will just take up a simple example of a single line in a C statement saying, so I am taking an example which is A is equal to B plus C star 10. So here we have taken a simple statement in our C language, and we'll see how this simple statements gets converted to a final machine language. So here this particular statement goes to our lexical analysis phase, which is the first phase in our compiler. So here the lexical analysis will be dividing this each and every phase into tokens. For example, say here A is an identifier and equal to is an operator, and B identifier plus operator, C again identifier, this multiplication symbol operator, 10 is a constant. So it will be checking for each and every individual unit, and it will be dividing into tokens, such that, for example, what are the identifiers, what are the operators, and what are the keywords, such like it will be dividing, and it will be storing it in a data structure which is called as symbol table. So with the help of the symbol table only, the front end of the compiler works and it executes into intermediate code. So here we will be getting it as this A is our identifier. So this is ID 1, identifier 1, equal to operator will be in angular brackets, and again identifier 2, we have a plus operator, and identifier 3, and we have a star operator and a constant 10. So like this it will be dividing each and everything into tokens, and it will be giving us. And after this particular lexical analysis, these tokens will be given as input to the next phase of compiler, which is syntax analysis. So the job of syntax analysis is that it has to check whether the particular statement is being correct with the program's syntax. For example, say in C language, for each and everything we'll be following few syntax. So this particular lines follows the syntax of that particular programming language is to be checked. So this will be done in the syntax analysis phase. And after checking for the syntax, it will be converting and giving us a parse tree, which will be helpful for the next phase of compiler, which is semantic analysis. So here it will be generating a graph structure, something like this. So equal to operator, actually we have to perform id plus 2, and we have to sum it with id 3 into 10. So here multiplication plays a higher priority, so we will be doing the multiplication operation, and the multiplication is to be done with 10, a constant, and a identifier 3, and the result of this to be summed up with identifier 2. So now the result of this is to be assigned to, that is with help of equal to operator I am assigning to identifier 1. So like this it will be generating a tree structure in our syntax analysis phase, once checking the syntax whether the statement is being mapped with the particular programming language syntax. So after this we will be giving this parse tree as input to the next phase of compiler, which is a semantic analysis. So basically the semantic analysis does the type checking process, and it will be checking for example say this 10, it could be type checked. So here assume that A, B and C identifiers are of floating point values. Probably the 10 could be also floating point value. Instead of integer, we have to make the 10 to be a floating point value. So this conversion could be done in our semantic analysis. So for converting an integer to float, we require int to float function. So this could be done in our semantic analysis phase. That is to be simple. The type checking process all will be done in our semantic analysis phase. So here we'll just get a modified parse tree like this. The only variation we have done into this particular statement is that we have converted the integer value 10 into floating point value. So int to float function should be applied for the 10. So when we apply that int to float to 10, we will be getting, instead of 10 we will be getting 10.0. that's all. So this is our semantic analysis. So next, after the semantic analysis, this particular is given to our ICG, which is intermediate code representation. So ICG is that which will be converting these parse tree into some 3 address code form, such that for each and every statement at least 3 addresses will be used. So here we'll just see what will happen. So here the first operation which we have to perform is that we have to convert this 10 to 10.0. So here for each and every operation what we will do, we will be using some temporary registers, that is we will be converting it into some intermediate form. Before, actually we will not be able to convert the particular statement into zeros and ones directly. So we will be converting that into some intermediate form. So one of the intermediate form here we are going to convert is 3 address code. So I am just assigning the first task, which is T1 is equal to into float of 10. So now 10.0 value will be stored in T1. So after this what we have to do actually, so this answer, particular answer is now stored in T1. So now I have to multiply the T1 with identifier 3. So after multiplying, I am storing the result in another temporary register named T2. And after this result is now stored in T2. So this result is to be summed up with identifier 2. So the overall result is stored in T2. So T2 plus ID 2, I am storing it in T3. So now here the result could be stored in T3. So the results of this summing is stored in T3. So T3 can be directly assigned to identifier 1. So T3 is equal to identifier 1. So this is our intermediate code. Once we have got the intermediate code, the next step what we have to do is that, so this could be optimized. So this step is to be optimized. So we have to perform our code optimization. So looking at the results after ICG, actually we have used 3 temporary registers. So when the temporary registers is being used more, the time and space complexity could be probably increased. So in order to reduce that, we have to optimize the code such that we will be trying to reduce the temporary registers we have used over here. So we'll just try to do the possibilities of reducing the temporary registers. So I'm just writing I am just multiplying identifier 3 into instead of doing this integer to float of 10, it is actually the result of int to float of 10 is 10.0. So I am directly applying the 10.0 over here to minimize the temporary registers usage. So now I am assigning the value to T1. So identify 3 into 10 value is stored in T1, and after this results, what I have to do, I have to sum this with identifier 2, and after the sum, the results should be stored in identifier 1. So I can do it directly instead of storing the results in T3, and again the results of T3 is assigned to ID1, and to just skip this step, I am directly adding the results and assigning to identifier 1. This could be done. This is code optimization, that is wherever possible we have to try to reduce the code, that is we here are just trying to reduce temporary register usage. So after this phase we will be going to code generation, that is where we will be getting this 2 lines of statements into mnemonics form. So here mnemonics could be given to assembler, and that is nothing but our assembly language. So then assembler will be converting this assembly language into zeros and ones. So here I am just going to apply code generation and going to see how these operations has been converted to mnemonics. So here mnemonics, in the sense we have to use multiplication, addition function, and what we could have been discussed in few microprocessor courses. So here I am just going to use some registers and do this operation. So I am just first I am going to multiply. Here I am using the first operation we have to do is multiplication. So before that we have to have ID3 value. So before that I have to load, since it is a floating point value, load floating point value. What we have to load? ID3 value into some register. So I am loading this ID3 value into R1 register, after which the value is stored in R1. So after this I am multiplying this value of ID3 stored in R1 with 10. So the 10 can be directly written with the hash symbol since it is a constant value. So R1 and this 10 should be multiplied, and the result is to be stored in again R1. And after this particular step, the multiplication result will be stored in R1. After that we have to actually add identifier 2, but we doesn't know or the system doesn't know what is the value of identifier 2. So first we have to load the identifier 2 value into some registers. So I am just doing load the floating point value of ID2 in register R2. So now ID2 value is stored in R2 and this multiplication result is stored in R1. So now we can sum up R1 and R2. So sum up in the sense we are going to add the floating point values R1, which is the multiplication result, and R2, which is the identifier 2 value, and after adding these two results I am going to store the result in either R1 or R2. It can be any one of the registers. So I am storing the result in R2, and after this we have to store the result of R2 in the identifier 1. So we can directly do as store the result of R2 in ID1. So this is a code generation phase where we will be getting mnemonics, and this results could be given to the assembler, and assembler will be converting this mnemonics into machine language. Thank you.